Okay, we're back. And you'll hopefully recall that we've been talking about limits that involve, infinity, the concept, the sideways eight, that kind of thing. So the last couple of videos were focused on what happens if the function's values approach infinity or negative infinity, while we let x approach some finite real number, 0, 10, 3, -2, what have you. What we're going to shift gears on at this point is looking at scenarios where it's the other way around in some sense. We look at what happens when we let our x coordinate, our independent variable, if you will, we let that run off to infinity or run off in the other direction to negative infinity, whichever way you want to look at it. In a like if you in a pre-calculus context, you might have heard this referred to as looking at the end behavior of a function. So our first example that appears in the notes file I posted in Moodle is sitting right here. I've also taken the liberty of a painstaking reproduction of my calculator's sketched graph of this thing for an appropriate viewing window. So anyway, so we have 3x to the fourth over the quantity x to the fourth plus 1. And this notion of end behavior, it's kind of like what I've drawn here, it doesn't really matter. Like I could kind of like put like a big censored bar over the entire center of my XY plane. And I want to know what's happening. Even here's maybe a little too close, like way over this way or way back out that way. So that's the idea of end behavior, and that's what we're considering here. You'll notice the definitions talk about what x is, or what our function is doing as we let x approach infinity in this direction, or negative infinity in the other direction. And you can kind of see what's happening with the graph. I didn't put in full tick marks, but from the sense of scale, you can see somewhere, a little, more than halfway between 0 and 5, it looks like this thing's flattening out. Same thing, over here. You can almost imagine sort of a, dotted line, like you might have seen in the past, for like vertical asymptotes, of, that it looks like our graph kind of keeps nudging ever and ever closer to this thing without actually touching it. Technically, it could touch it. It could theoretically just kind of like wobble up and down forever, so long as the values kind of keep pinching down on that thing. So you've probably heard this referred to as a horizontal asymptote in the past. Like I said, with vertical asymptotes, I've pointedly avoided that language because without limits in calculus, it's kind of hazy on how to define what those asymptotes are. But yeah, it looks like this thing has a horizontal asymptote at y equals something or another. Like I said, I haven't pinned it down here. If you tried playing around with a number here, let's just plug, like, say, x equals 10 into this thing. So if x is equal to 10, 3 times 10 to the 4th, that's going to be 30,000 up in the numerator. Down below, x to the 4th, for a value of 10 would be 10,000. We have 10,001. So, real quick, let me fire up my favorite calculating device and work out what 30,000 divided by 10,001 is. So I'm having to round here, but it's 2.9997. So now, the idea is 10's not even really that far away from the origin in the grand scheme of things. What if I plugged in like 100? Then we're talking about a much larger number. 100 to the 4th is 10 to the 8th, so that's 100 million. So we're talking 300 million over 100 million and 1. You can work out what that is and keep plugging in even larger values. Your calculator's table feature, as I've mentioned before, is awesome at generating these things without costing us a ton of effort. What you'll end up noticing is, in the grand scheme of things, if we let x get big enough, I've talked about this in the positive sense. Same thing is applying in the negative sense, because the even power here gets rid of any minus signs on our x value. This adding 1 becomes more and more meaningless the bigger x is. As I said, 300 million over 100 million and 1 is essentially the same thing as 300 million over 100 million, which would be like 3. So we haven't methodically proved that this is the case, but based on the picture, based on what our numbers are telling us, it looks like the limit as x approaches infinity, also as x approaches minus infinity. I got ready to write infinity again. We just said that doesn't, that's not what's happening. So it looks like our function is getting closer and closer to 3 as we push x bigger and bigger and bigger, or more and more and more negative. Saying smaller is always kind of rankled me. It's like that you might misinterpret that as meaning close to 0. Anyway, so as the notes file says, if we have a limit like this, as you say, a limit as we let x get really, really big, or as x gets really, really, really negative, then that dotted line I drew in, the horizontal line y equals 3, is what we would call the horizontal asymptote for this particular function. All right, so moving on in the notes, we got a few examples where we kind of separate from talking about asymptotes to talking specifically about limits. So I'm giving you a moment to clear this off, and then we'll dig in. All right, so breaking in with a relatively painless example. So we've got 3 minus 2 over x to the 4th. All right, so technically we can kind of use our limit law thing. So I haven't explicitly proved that, but it would work so long as all the limits exist. That we can consider this guy and then this guy and then take the difference of the two individual results. Now, as x gets larger and larger and larger and larger and larger, and you get the idea of, does 3 care? Not really. 3 just wants to be left alone and get to be 3. So that part is okay. Now here's the kind of the point of this particular part of the process. Again, as we let x get bigger and bigger and bigger and bigger and bigger, or x to the 4th is going to be even bigger than that. Like I said, for x equals 10, we were already up at 10,000. If we go up to 10 million, you get the idea. The denominator of this fraction is getting huge, massive, beyond human comprehension large. We're talking like astronomical scales kind of thing. Up top, we have 2. 2 divided by a billion is really, really small. 2 divided by a quadrillion is even smaller. You get the idea. The further out we push x, the smaller this guy is getting. So in terms of a limit, it's really getting, he's shrinking down to 0. So our overall limit in this instance ends up being 3. All right, so that's one example. Let's take a look at the next one real quick. So we have some variations on a rational function right here. If you'll notice the next 3 examples, if you don't look real closely, you can't quite tell the difference between them. So we have 2x squared plus 5 over 3x squared plus 1. And once again, we're looking at what happens as our limiting, or as our x coordinate runs off to infinity. So like I said with that very first example, you can imagine plugging in numbers. Feel free to test this numerically. But in an analytical sense, these constants here at the back, they have less and less impact the bigger x is, right? By the time, you feed 100 into this thing. 100 squared is 10,000 again. So you had 20,005 over 30,001. You keep going bigger than that. You plug in, thousands, millions, billions. You see how this is going. The further down the line we go, the less impact adding 5 or adding 1 is really having on things. So these terms are what we would call dominated by the higher exponent terms that they're stuck with inside this fraction. So this is not precise mathematical, nomenclature per se, but I've always kind of done like a little twiddly thing here to say we can really at this stage zero in on our highest exponent terms. So in this case, it's going to be a 2x squared and a 3x squared. And if I had just given you this, most likely what you'd have done is you've dropped back into algebra 1 mode and say, oh wait, slash, I can cancel those. from a functional standpoint, it's not even really wrong here because we're not considering x equals 0 where something could go wrong. It's just, these two guys. So, yeah, sure. Cancel them away. They're gone. And then all that we're left with, those marker strokes weren't really visible there. Anyway, and as it turns out, this, is now just the constant 2/3. Kind of like the 3 in the previous example, he just wants to be left alone. I mean, it just wants to be, it just wants to be 2/3. And again, you can check the numerical or the graphical representation of this will end up, verifying that same kind of behavior for you. So we've seen a couple of these guys now. In the interest of, trying to keep this, flowing, okay, I think I'm going to break off for now and make a separate video with the last two examples, kind of bring it home and then talk about the very end of this notes file. So thanks for watching.